Here we are for Electrostatics Worksheet 3, Problem 1, which asks, given the mathematical representation of Coulomb's law, F is K Q1 Q2 over R squared, where K is 9 times 10 to the 9 newtons meters squared per Coulomb squared. Describe in words the relationship among electric force, charge, and distance. Pretty much what we're all just talking about here is looking at those mathematical models of how these variables relate to each other. So when I look at Coulomb's law, pretty much what I'm saying here is I want to find the relationship between force and these other two quantities, charge and distance between the charges. And pretty much I'm just saying, hey, that electric force is proportional to the charge. And so you say with that is what we call a direct relationship, or directly proportional. So if I double the charge, I would double the force. Triple the charge, triple the force, direct relationship. Same thing for Q2, directly proportional. And then for that distance, that separation distance, you can say this one a couple different ways. You can say that FE is directly proportional to 1 over the distance squared. Okay, so again, we can say directly proportional. Or you can say that FE is inversely proportional to R squared, right? Sometimes we call this kind of relationship an inverse square relationship, is the other way you see it stated. And it's actually like a really common thing in physics, that things have an inverse square relationship with distance. I don't know if, we talked about in class this year about how if you have an object, like say, we talk about having a big mass, we talk about how its gravitational influence kind of spreads out in space around it, where it'll pull on other masses around it. And we said, when you draw in that gravitational influence, we call it a gravitational field diagram. We talked about how the field is strong when the field lines are close together and it's weak where they're far apart. And we recognize that if you think about the field strength then being directly proportional to how closely, directly related to how closely spaced the lines are, you can say that that field strength is going to be equal to the number of field lines over the area. If you think about, and this is kind of a weird thing to think about, what I mean by area is if you imagine drawing a bubble around this thing, like a sphere, right? These field lines are coming at it from all directions. And you count, you say how closely packed the field lines are to tell you how strong the field strength. It's like if you imagine having like a square meter of area, how many field lines are punching through that square meter area, it tells you how strong the field is. And so we said that, look, if I draw a bubble around it, say it's a distance r away, then my area would be the surface area of a sphere, 4 pi r squared. You say, what happens if I make the bubble like twice as far out? At 2r? Well, I'd have the same number of field lines punching through it. But now that it's the new area, it's 4 pi it's 4 pi r squared again, but now with a different r. So the point is my field strength would be getting weaker as the area gets bigger. And you say that area, as the area gets bigger, it's the same amount of influence, but it's spread more thinly. And you say, as it spreads out over a bigger surface area sphere, that's just the way it spreads out in 3 dimensions. We expect that field strength to be proportional to, then, 1 over 4 pi r squared, the surface area of a sphere. And that's what we see with gravitational fields, with electrical fields, with magnetic fields. We see it with, if I have a source of light, and the light radiating out in 3 dimensions, it gets weaker, proportional to 1 over 4 pi r squared. And also with like a source of radiation, radioactivity, like it gets weaker as you drop out. So this inverse square thing really just comes from the geometry of 3-dimensional space. As things spread out in 3D, they get more and more spread out and get weaker and weaker, proportional to 1 over 4 pi r squared. All right, that's it for problem 1.